Okay, so the problem we face is in statistics, a trick is pulled about a third to two-thirds of the way into the course. It's all according to which statistics class you're taking. But in a class like this, sooner or later it's coming, and usually about now. And that's when we move from things that look like relative frequency histograms and frequency histograms to something called density distributions. And that's what I'm explaining now, is why are normal curves and other curves like that treated differently? Probability density functions, why are they treated differently than we've been treating histograms before now? And they are treated differently, and quite frankly, like our textbook has 2 sentences to say about this. All the rest of it's just kind of fluff, but 2 sentences explaining what's happening. So I want to explain that to you right now. Okay, so let's get to work. That's our problem. All right, so let's get my face out of there. So I went to the IRS and I got some data. I looked up all the data for 2017 on their tax returns. So for all the 27,000 plus zip codes, it divides up the tax returns and gives the average tax returns for all sorts of things that you put on the tax returns. Just all this data that you can grab. And what I grabbed, let me open this up. What I grabbed, so here's where I'm grabbing it. You don't need to know any of this. I just think it's worthwhile seeing it. And I grabbed it. What you're looking at here is the salaries, the average salaries for each of the 27,000 plus zip code zones in the United States. So you notice I do a box and whisker plot, but a huge number of the zip code salaries are considered outliers for this. Notice this little squeezed in box right here. It's covering most of it, but all these dots here are considered outliers. Why? Because most of us live in one kind of area when it comes to a salary. Now, I'm not doing wealth. I'm not doing other kinds of income and dividend income or anything like that. I'm just doing salary and wages, okay? Even then, there's a big difference, a big split in salaries. So what I did was I took a look and I realized that when 95% of the salaries listed, the average salaries for each of the zip codes, 95% of the zip codes had the average wage being below 100,000. And it's around 100,000. It's very close to 100,000, and 100,000 is a nice cutoff mark. So about 5% of the zip codes have an average salary, average wage above 100,000, and 95% of the other ones have an average. So there's lots of zip codes that have people who make more than that, but on average they're making less than that. Okay, so that's what I'm dealing with, is I chopped off all the zip codes, and now how many zip codes do I have less? About 26,000, because I told you 95% of the zip codes have average salaries below 100,000. So let's review and look at some frequency histograms. So here's one. Now notice I am not using StatsCrunch. I am using Mathematica because I can make them pretty. The idea here is not for you to compute things, but for you to see some things and to learn some things. So here I have a frequency histogram using bin sizes. I start at 0, go up to $100,000 a year, and I have bin sizes of 5,000. And here is a nice histogram of that. All right, now if you'll notice right below that, I've got the box and whisker plot with a little kind of like this diamond-y shaped thing right here is the mean. So yes, we are skewed. Which direction are we skewed? We're skewed right. We're stretched right. We're skewed right. All right, so there's a bella shape here that we've been talking about, a bell-like shape, but it's kind of pulled and stretched to the right. Now what I want to do is show you different histograms. But I'm going to go ahead and change. What we'd like to do is be able to get a histogram that no matter what our bin width was, they looked kind of the same no matter what. So we're trying to regress down to that shape, to kind of capture that shape without it really mattering what the bin size is. And that's tough. So first of all, I'm going to go to a relative frequency histogram, which won't change this. It will just change this to be numbers between 0 and 1. So let's do 5,000 relative frequency histogram. So this is a relative frequency histogram with bin widths of 5,000. Now, I just want to take a peek at what the relative frequency histogram would be with bin widths double that, at 10,000. So that I'll have less bars and it'll be twice as thick. Let's take a look at that. There they are. Oops, some of the code got through. Basic shape, but so here the range is going from 0.0 to almost 0.5, and up here the range is going from 0 to 0.25. Why? Well, when the bins are half the width, their heights, there's more bins, so their heights are not as high, because remember, the height of each of these bars is the percentage of all of the things in that bin that's represented. So like this one right here, 22% of our data falls in this bin right here. So when we're with a bin width of 10,000, we've got almost 40% of the, and actually it tells us 38.26% of the salaries are between 40 and 50,000. Okay, let's go the other direction. What I want to do is have bin widths of 1,000. Now, if I just keep this same Y, actually if I keep the Y-axis like I had for 5,000, and I run my program and it generates the histogram, the relative frequency histogram of bin widths 1,000, look what I get. And why? Because when I run this, the heights are different, because now I'm going to have 5 times as many as I had when I had bin widths of 5,000. So the percentage within each bin drops drastically. So I need to rescale the Y-axis, and I do that. So let's rescale it. There we go. Now, our eyes, we can't help it. We're human. We definitely see a shape there. We definitely see a shape there. Now, I want to come back to that. This is probably, this histogram probably illustrates the shape that we're shooting for more than any other picture. But let's keep making the bins smaller and smaller and see that, remind ourselves some of the silliness that happens when we make the bins too thin, just like when we make the bins too big. So now I'm going to keep the same scale from 0 to 0.06 to 6%. So my scale goes from Y scale goes from 0 to 6%, but I'm going to shrink my bin width to, I think, 100 instead of 1,000. I do. And let's look at what happens. Whoa! Now the height of the individual bins are less than 1% each. So I need to adjust for that. And I do. There we go. So we still see that shape, but now our bins are thin enough where just a few added salaries that land in that little bin can change the percentage enough pretty drastically compared to the other bins. So we still see the signal, the shape that we would like to regress to, but now we're seeing more noise. Now we're seeing more noise. More information, but it's noisy information, okay? I'm going to go one more just to see what happens. So we're going to go from 100 bin widths of $100 to bin widths of $10. All right, so you can be in a different bin than your neighbor. Well, no, because your neighbor is probably in the same zip code. But 2 zip codes can be in different bins if their average salaries differ by more than $20. Okay, for sure. We'll be in okay, so. But we'll keep the same Y just to see what happens. So once again, my Y needs to be adjusted because I've decreased my bin widths by a factor of 10. All right, so now we need a Y that goes at most 0.1%. No bin contains more than 0.1% of all the zip codes. So, and this is the last of the histograms. It's just nice to walk through all of these, and I will post all of this in a PDF that's got all these pictures so that you can check it out. Now I am seeing these artifact lines that are showing me these bins are literally stepping up one at a time. So I'm I am now at probably the lowest I would ever consider going, where things are very noisy and I just barely see the signal in there, the shape in here. Okay? Now, I want to talk about what the problems are that we're having and the question I want to ask. So here's the problems. So as we change the bin widths, we can either get really clunky bins where things are just flat and have a few different heights, or they can get really thin and get really noisy. Look like all these hairs coming up. Okay? And in either of those end cases, when we get towards the middle at some sweet spot, and even at the end cases, we notice this kind of curve that's going on, the signal that we would like to regress this information down to. Okay, so here's my question. There's a shape that we see, especially back, let me go back to the one that really I thought stood out. That shape that we see right there. What is it? And how do we get to it? There's a shape that the histograms take on for a lot of bin widths. How can we capture or regress to that single shape? Okay? Now, statisticians / mathematicians have an answer for this, and that's what I want to talk to you. Okay? So here's a good chance to just stop and break and think about what we're doing, and then we'll start up again. Okay. I kind of cut myself off there. I was going to say, all right, I'm going to take a little break. But what I've got up here now, remember our question is, well, remember you just heard it, is what is that shape? How can we get a picture of the shape that these histograms are forming without just tracing it out and kind of eyeballing it? And this is kind of a regression problem like we had earlier, where if we have a cloud of scatter points and we want a model that kind of regresses the data down to a single edge, what if we got a distribution, some type of histogram, and we would like it to regress down to something smooth? How do we do that? It's not that obvious. Okay, but here's a picture, and I used one of our known techniques to get it as the distribution that we're seeing, or an estimate of the distribution that we're seeing in that data of those different histograms. And I'm going to compare this shape to the histograms that we have in a second. But the idea is this. Instead of thinking of each data point as a single value that's a little value that sits in a bin, so you make a bunch of bins across the x-axis. Hold it, let me blow this up. So you make a bunch of bins along the x-axis, and you say, okay, how many items are in, how many data points fall in here, and then you make a bar with that height of the percentage. 5% fall in here, 13% fall in here, 2% fall in here. Instead of doing that, what if for each of the little data values, in our case salaries, what if we thought of the curve as a board, and we're just going to pour a little bit of sand, the same amount of sand, at each of the points where we have a data value. So where we have more salaries, we're going to pour more sand. Where we have less salaries, we're going to pour less sand. And suppose that however much sand you decide to pour, we're going to back up enough so that the total amount of sand can be thought of as one unit of sand. Then what you get will be this kind of smoother picture of what we got. And I want to show us doing that. So what I did here, let me back my ugly face out of there. What we did here is I took the first, we've got a little over 26,000 zip codes, zones we're looking at, the wages from 26,000 zip codes. So the first 500 zip codes I took and just poured out a little bit of sand for each of them, and that's the shape I got, what you see on the screen right there. Okay? Now I'm going to do that for each one. So pour a little, pour a little, pour a little, pour a little, pour a little. So 500 at a time, this is, and then we go to that final one. This is 53 steps, but as I pour it on, notice more sand is kind of coming over here. Now we're not thinking about the physics of sand, so we're just we're assuming the sand stays pretty tight, but it spreads out over the last sand, okay? And I keep pouring, I keep pouring. Now, I'm not saying it's obvious how I did this. I'm just saying think of it this way. And then when we're done, when we finally pour out the last of the sand, 1 unit of sand is sitting here. Now, here's the question I have for you. What geometric property of that curve corresponds to how much sand I poured? I'll say it again. What about this curve corresponds to how much sand I poured? All right? And the answer is the area. I've got the heights showing, but the heights mean nothing as far as this curve is concerned. It's the area that's important. Now, to make sure you understand that this thing is just lots and lots of layers, I actually did a little something for you. And I don't know if it's going to help you at all, but it sure is, I think, looks interesting. Here is the end result of pouring, and I just drew a little blue line, and it calculated a little blue line for all 53 layers of 500 zip codes at a time, just building up, layer after layer after layer after layer, until I had 1 unit of sand lining up. So I claim this technique, not that you can do it by hand. I don't want you doing this by hand. Just give for granted that this kind of thing can be done. So the answer to our question is the following: that an alternative to a frequency or a relative frequency histogram is something called a density histogram, where instead of the height of the bars, instead of the height of the curve in this case, having any direct meaning, do not look at the height to mean anything. It's the area of each of the bars that represents the proportion, or it's the area over any bin that represents the proportion. And notice that's what area does. I can pick any bin here now, any distance, and I'll do that for you. Like I could say, how many salaries lie between 30 and 80,000? Well, if I had some technique for computing area, it's the area. It's the amount of sand that's between 30,000 and 80,000 K. Now, I will tell you, in calculus, we spend time. Part of calculus is spending time talking about area and what that has to do with rates. And we actually learn the classical primary tool for finding areas of curves just like that. That's neither here nor there. So I've got a little note here. Let's take a look at this note. And I've said this a couple times, these density histograms are not something you would do by hand. There's not something you would ask Stats Crunch to draw by hand. Though I bet, no, it doesn't do the free curves regardless, okay? But a density histogram is when you make the bars, the area in the bars, be the percentage, the relative frequency, not the heights. And when you do that, then no matter how small or big you choose your bins, the Y values stay the same. So you don't get all this weird scaling issue. And I'll show you how it matches up with this curve. So the total area and the total amount of probability sand is 100% proportion sand. And let's see, calculating the area over any interval, let's type that in, will be the proportion of the data in the interval. So if you compute any area you want over any interval, that will be how many data points lie in that. So in a sense, the area can store a lot more data all at once. It's a much more useful tool. And this is actually, in science, this is what we mean by density, just like slopes is what we mean by rate. Okay, let's go back and look at those real quickly. Look at those. So here's the 10,000 bar, and behind it I drew, now each of these bars, I'm using the area. The total area of those bars is 1. The area of each bar represents its relative frequency, not the height, but the area. And when I do that, they all can be matched up against this final curve. And notice it matches nicely. I drew it behind there with a little opacity. Okay, let's do the next one. What was the next one? This is 10,000. I think the next one is 5,000. Oh, it says it right there. My microphone was in the way. There's 5,000. Wow, that looks good. The area of each bar. If I were to quiz you, I would say, what does the area of each bar of a density histogram represent? The area of each bar represents the relative frequency for that bend, not the height, the area. So you would make the height so that the height times the width, height times width, is area. And that's the secret to keeping the y the same. Notice y goes up to 0.00005 still. All right? And the y doesn't even really matter. All these histograms, because they're density histograms, you could call them area histograms, all have the same basic size. Okay, let's do 1,000. I think you're going to like this. Look at that. It's exactly the thing we want. You should be saying, good grief, I have got to go study some more math and some stats so I can find out where in the world did he get that curve? How did he figure that out? Oh my goodness, I have stats, love. Woo! I got to get that. I got to find it. And maybe not. But if you do feel that way, I am sure Dr. Taylor can help you out. All right, so there we see that the area for each of these bars adds up to be 1, but because it's kind of jumping around and hairy, it doesn't quite line up with that blue is where all those bars would compact down to. And for the 10. Now, okay? Now, use. Why would I do this other than it does capture it's kind of like the single best way of representing things in it, and it makes the scaling for the y-axis correct, even though it's harder to do. Well, I'm going to show you why. So suppose I asked you, what proportion of all these average salaries fall between 40 and 70K? Well, if we use this density distribution here, representing that is easy. It's the area between here and here, between $40,000 and $70,000. And I actually went through and calculated what that area was for this curve, how much the area to the left was, and how much the area to the right was. You are not supposed to know how to calculate those. That is what you are learning in class with the x-bar plus or minus, and when we use z-scores, that is different ways of calculating area. You do not know how to find those areas. What I'm trying to make you do now is make a connection between these proportions, the percentages, these relative frequencies, and the area of the curve. All right? There's no calculating right now. No calculating. Okay? So, what do I have here? I have a picture. And it says that the proportion of these zip codes that have salaries between 40 and 70,000 is 62%. Now, what Dr. Taylor did in class is she asked the question, she told you about a theorem that says that if in life, one of the curves we see a lot is something that matches a very specific curve we know called the normal distribution, the bell curve. And this is almost bell curve, but skewed. And as a matter of fact, this still meets pretty well the empirical rule. And the empirical rule is that for almost anything in nature that we find, if it's exhibiting the bell curve, it probably is normally distributed. Meaning if we made a density histogram, a density distribution, a smooth version of the histogram, it would be one of the bell curves. And that if you found the mean, it would be right at the peak, though that's not true here. And that if you looked at one standard deviation in each direction, and I'm going to blow this up, make sure you can see me. It says that if you have a bell curve and you start at the mean and you move one standard deviation in each direction, so you've got x bar minus s and x bar plus s to give you two numbers, then usually the area under the density histogram, the density distribution, will be about 68%. And to interpret that means that about 68% of all your values will fall between those two numbers. And if you go two standard deviations in each direction, then you've got what? 95%, was it? And then 3 standard deviations is like 99.7, i.e. almost all of it. Okay? All right. I'm going to put up some more videos from other things about how to do some calculations, but this video is all about what? How do we transfer from looking at the height, the curve values, to looking at the area? And that's what you do in statistics. That's what we do in probability. It's the area under the curves that matter, and that's going to be true from now on. Learn it. Talk to you later.